Okay, today we are looking at chapter 26, Velleman DeVoe, which is about chi-squared inference procedures for distributions of categorical variables. Okay, chi-squared distributions are appropriate to model sampling distributions for counted data of categorical variables. If you only have one count being compared to one expected, you can actually use a one proportion z-interval or test if the conditions are met. Okay, but in chapter 26, we usually didn't have just a single count or a single um, proportion or whatever. We're using a list of counts. Okay, so that's why we use chi-squared. Conditions that you need to check for chi-squared inference include you want to make sure you have random sampling or assignment, that you have counted data, not percents or means or something like that, and that all expected cell counts are greater than 5. We'll talk more about expected in a minute, but just make sure that when you're checking this condition, you're checking the expected values, not the actual observed values. Okay. Now, if the expected cell count is violated, you may be able to fix that by collapsing the table, like combining two categories or something, if it would make sense to do so, and then be able to go ahead and redo the whole inference and all that with your new table. There are three different kinds of chi-squared tests that we learned. The first one was goodness of fit. If you have one set of counts for one variable that are being compared to an expected distribution, then you're using the goodness of fit test. Okay, so if you have like a one-way table. Now, if you have multiple distributions for a single variable, and one way to tell that you have this, if you have basically a single question asked in a survey, but you have different groups answering that question. Okay, so you might have different responses. Then that calls for the chi-squared test of homogeneity. Now, if you have two variables, so this would be represented by two different questions being asked at a survey, for example, compared against each other in a two-way table, then that calls for the chi-squared test of independence. So the chi-squared distribution, it doesn't look like the normal model or the t-distribution. It is skewed to the right, and all of its values are positive. So it starts at 0, and then it's skewed to the right. And so when we want to calculate our test statistic on this distribution, this is how we do it. Okay, so you take your observed count minus what's expected, and you take that difference and you square it. And you divide that by the expected number. You do that for every cell in your table, sum all of those up, and you have the chi-squared statistic. Okay, there are degrees of freedom for chi-squared because the exact shape of chi-squared does depend on the sample size. The degrees of freedom for goodness of fit test are calculated by taking the number of categories minus 1. Be very careful not to do sample size minus 1 here. Right, so it's not like the number of M&Ms in the bag minus 1, it's the number of colors of M&Ms minus 1, so just be very careful about that. Degrees of freedom for homogeneity and independence tests, since that's a two-way table, it's the number of rows minus 1 times the number of columns minus 1. And when you're calculating those, you don't include the table margins in those numbers. Okay, so here's an example. Here is a two-way table. This two-way table could be used for a test of homogeneity, because basically it looks to me like we would have a single question that might have something to do with about how they're investing their money or something in stocks, bonds, or cash. But then we have different groups responding. So it's one question. So this would be a chi-squared test of homogeneity that we could possibly do for this table. Now these here are margins. And so when we calculate the rows minus 1 times columns minus 1, we're not going to count any of these totals here. So the columns, there are 1, 2, 3 columns. Rows, there are 1, 2, 3, 4. So we take rows minus 1, so that's 3, times columns minus 1, that's 2. So 3 times 2, we would have 6 degrees of freedom. Okay. All right, now how do you do a chi-squared goodness of fit test? Well, it depends on what technology you have. Technically, you could do this by hand, but it would take a while. Okay. So if you have one of the calculators that has a newer OS, then all you have to do is put your observed counts in list 1 or whatever list, and your expected counts in list 2, and then run the chi-squared goodness of fit test located in the stat test menu. Now if you have an older calculator like a TI-83, it may not have that test. And so here's what you do. You put your observed in list 1, your expected in list 2. And then in list 3, go up to the name of the list and then put in L1 minus L2 quantity squared divided by L2, right? So observed minus expected squared over expected. Hit enter, and it'll put all of your chi-squared test components into list 3. And then go to second stat math, and there you'll find the sum command. And so then you can, on the main screen, choose sum of list 3. That'll be your chi-squared statistic. Okay, once you know that number, then you go under the distribution menu, and you can do chi-squared CDF, your test statistic, comma, some large number to represent infinity, comma, degrees of freedom. Okay, so let's take a quick look here on the calculator. All right, so I think this one is probably going to have the, all right, wake up. It's kind of sleeping. Wake up, wake up, wake up. Okay, so we go under stat test, and we scroll down, and we're going to look to see if this calculator has the chi-squared goodness of fit test. Okay, so keep going, keep going, keep going. This is not chi-squared goodness of fit. This one here will work for homogeneity or independence. Here I do have chi-squared goodness of fit. And so it's going to ask, where did you put your observed data? Where did you put the expected counts? And what are your degrees of freedom? And then calculate. Okay, now if you don't have that, not all is not lost, right? You just put your observed and your expecteds in list 1 and list 2 or wherever you want them. Then you go over to list 3, and up in the name of list 3, you could put, parentheses, list 1 minus list 2 quantity squared divided by list 2, which are your chi-squared components. Okay, then go back out to the main screen and go into stat math, second stat math. That's where the sum is. Whoops, went too far. And list 3. Okay, so there is my chi-squared test statistic. Now that I have it, I go into the distribution menu, and I'm looking for chi-squared CDF to find that shaded area from that test statistic or greater. So I can go second answer, right, comma, big value, comma, whatever my degrees of freedom are. Let's see, I think I had 7 values in the list, so it would be 6 in this case. Okay. So sometimes you'll get a 0 when it's extremely unlikely. But if you do get that, just check and make sure that you did the number of categories for degrees of freedom and not the number of counts. Okay? All right. So that's goodness of fit. So what about homogeneity and independence? How do you do those? Well, everybody does this the same way. You put the table in question in matrix A, not including any of the totals, no margins. Then you run the chi-squared test under stat test menu. And then make sure you go back and check in matrix B to see if there was an expected cell count condition violation. And then make sure you report the chi-squared statistic, the degrees of freedom, and the p-value to make your conclusion. Okay, so second x to the negative 1 is where matrices are. And if you want to put something in, you need to go to edit. So I'm going to edit matrix A. Let's say I had 3 rows and 3 columns. And then you can put in whatever the values are from the table that would be provided. I'm just making up some numbers here. Okay, and then you would go to stat tests and find the chi-squared test. All right, and then you would say the observed I put in A, this is where I want the expected in B, and then you would say calculate. And so I have a chi-squared statistic, very small, 2.13. Usually chi-squareds are much bigger than t's or z's. P-value of 0.7, so very high p-value, we would fail to reject the null. Degrees of freedom is 4. Now I need to go back and look at matrix B. Okay, so one way to do that is just go into, like, you're going to edit it and see what's there. And I do have some cell count violations, right? These should all be greater than 5. And there are several that aren't. Okay, so I would not be able to continue with this because there's just too many here. You know, I don't think, I'd have to know what this was all about to see if maybe I could collapse some of the table. But I've got an expected cell count violation in every row and in every column, so it's very unlikely that I can fix this. I would really need a bigger sample size to solve this problem. Okay, so that's how you do homogeneity and independence testing. Now, how do you write the hypotheses when you're doing your hypothesis test? For goodness of fit, you know is that the distribution for blank is as expected. You may be a little more specific by saying what the expectation is. For example, the distribution for colors of M&Ms is as reported on the M&M website. Okay, the alternate, the distribution is not according to what's reported on the M&M website. And then you might say how it is reported. Okay, for homogeneity, you would say for your null, there is no difference in the distribution of blank for the population's treatments blank. So for example, there is no difference in the distribution of investments for different age groups. Okay, and the alternate would be that there is a difference. And then for the chi-squared test of independence, your null would say there is no association between blank and blank, and your alternate would say there is an association. So there's no association between income and education level or something like that. Okay. Now, you can also word this one as, for your null, they are not independent for your null, and then they are independent. I don't recommend that because it kind of confuses people, because which one is not is kind of reversed from all the others, right? On these two, the alternate is not as expected, okay? And then we have no difference, there is a difference. No association, there is an association. So just to be consistent, sometimes I think using the association one is better. But it is up to you. Just be very careful to word them correctly. Now, what do you do if you reject the null? Okay, if your p-value ends up being so small that you do reject the null, then you should look at each of the components in the sum for the chi-squared statistic, so each observed minus expected squared over expected, and see which are the largest, and you should comment about which one or two are largest, and thus were the largest contributors to rejecting the null. So for example, if I go back to these lists here, these are all of the individual components of the chi-squared test statistic, and if we look here, they're getting larger as we go, right? This is the largest one, so this was the largest contributor to that chi-squared test statistic of 505, so it was the largest contributor to me to rejecting the null. Okay, so whatever this particular data point is about, it was the most different from expected out of all of them. Okay, right, which you can see here, if these are all of our expected, definitely the most different from 0.1667. So it was the biggest contributor to rejecting the null. It's a little bit harder to find these if you're working from a table, but you certainly can do that. And let's talk about how do you do that. So if you're working with matrices, how do you supposed to be yellow? And then you take that percent of the total to find the expected count. Don't round those to whole numbers. For homogeneity dependence, you use the totals or margins to figure out what percent is expected, and then you find that percent for the category of interest. So for example, if we go back and look at that table again, here are our totals here, right? So I could say that 62 out of 236 is the proportion in the 35 to 44 age category. So 62 out of 236. So go back home. 62 divided by 236. So that percent of, so now I'm expecting that percent out of 125 to be the expected number for this cell here. Okay, so I go to times 125, and so I get an expected cell count of 32.8 for this cell right here. 62 out of 236, 32.8 out of 125 is the same percent. And then to do observed expected squared over expected, I would just take 35 minus that 32.8 quantity squared divided by 32.8. Okay, and so you can find those. You could use the list to help you with that. And that concludes chi-squared.